In the last class, we've been talking about perfect fields. Today, we are going to discuss an important theorem. It's called the primitive element theorem. This is a very important theorem in the whole field theory also. So let us state the theorem first. Let E be a finite separable extension of F. Then there exists an alpha belongs to E such that E is the simple extension of that element. Give an example. Let's take E is equal to Q of root 3 comma root 2 and F is equal to Q. Then there is an alpha in E such that E is equal to Q of alpha. We are going to do this problem, so I'm not going to compute the value of alpha at this moment. Once we are done with the proof of this theorem, we'll come back and do the same problem. So what is happening here is there is a Q here, so Q of root 2 comma root 3. This actually depends on two values, root 2 and root 3. Then the same field can be expressed as Q of some alpha. And that alpha is called primitive element. So this alpha is called the primitive element of E. So there are two situations here. It only says that E is a finite extension of F, but doesn't say that F is finite. So we'll have two scenarios. One is F is finite, and the second one is F is infinite. And in fact, the example we took is when F is infinite. So if F is finite, that implies E is finite. But if E is finite, then E star the group of elements from group of non-zero elements from non-zero elements from E is cyclic. E is cyclic. We already know. And say with the generator alpha. Then E is equal to f of 1. So that is simple. When f is finite, it is simple. Now let us assume that f is infinite. So what we need to do is, this is a finite extension, so you can always say E is equal to f of alpha 1 dash dash alpha n. And we want to show that there is an alpha in E such that E can be expressed as f of alpha. So what we are going to do is, instead of taking n elements, we'll assume that there are two elements. Let E is equal to beta comma gamma. Then we are going to find an alpha such that E is equal to f of alpha. And you can extend it a number of times. So what we do is, let beta gamma belongs to E. So because E is separable and it's a finite extension, both alpha, beta and gamma are algebraic. So we have irreducible polynomial corresponding to these two. So they are irreducible polynomial of finite degree. So we'll assume that let beta 1 dash dash beta n be the zeros of irreducible polynomial of beta comma f, and gamma 1 dash dash gamma m be the zeros of irreducible polynomial of gamma over f. And assume that beta is equal to beta 1 and gamma is equal to gamma 1, because beta is one of these and gamma is one of these m variables. So we are assuming that there. Now f is infinite. So you can always choose an element A in f such that A is different from beta I minus beta divided by gamma minus gamma j for all I and j not equal to 1. You can always choose an element like this because this is a finite number of combinations and we are taking A from an infinite set. It's always possible. So this implies our aim is to construct alpha. Okay, so we are going to construct alpha using this A. So this implies A gamma minus A gamma j is not equal to beta I minus beta. And that implies beta plus a gamma is not equal to beta I plus a gamma j for all I and j not equal to 1. Now we are going to construct that element alpha. Let alpha is equal to beta plus a gamma. And let h of x equal to, or we'll say, first we'll define, let f of x equal to irreducible polynomial of beta over f, and h of x equal to f of a minus gamma x. Sorry, not gamma x. Yeah, a minus gamma x. No, actually this is going to be alpha minus ax. Now where is this f? F of x belongs to f of x. And replacing x with alpha minus ax. What does that mean? That means h of x belongs to f of alpha of x, because the only difference between h of x and h of x is the introduction of alpha. A is already in f, so alpha is not in f, it is actually outside f in E. So when we are replacing x by alpha minus ax, this polynomial will be in here. Now let us compute h of gamma is equal to f of alpha minus a gamma. And what is alpha minus a gamma? What is alpha? Alpha is beta plus gamma beta plus a gamma. So alpha minus a gamma is beta, and that is equal to f of beta. And what is beta? Beta is one of the zeros of f of x, because f of x is the irreducible polynomial of beta. So this will be 0. And that implies gamma is a 0 of h of x in f of alpha x. I want to explain one more thing before we go ahead. See, if there is an f here and there is an e here, if there is an element here, like let's say a, then its irreducible polynomial is x minus a. If an element is inside f, its irreducible polynomial will be linear. Linear means the power of the polynomial is 1. The degree of the polynomial is 1, maximum degree. So And here, this is the only 0 of h of x. And gamma is the only 0 of h of x. Why? Because if this has to be 0, f of this should be 0. Meaning this has to be one of these bi's. Then only this will become 0. And we already showed that b plus a gamma is different from bi plus aij for all I and j. And j different from 1. So with this condition, there is only one element here that make f 0. So that means gamma is the only 0 means, that means the irreducible polynomial of gamma over f of alpha is linear. Right? And because this is h of x belongs to f of alpha of x. And that implies gamma belongs to f of alpha. With the result I showed you that. If this is linear, then this belongs to f of alpha. So what we need to prove is construct an element alpha and show that beta and gamma belongs to f of alpha. If beta and gamma belongs to f of alpha, that means f of beta comma gamma is equal to f of alpha. We have already reached gamma belongs to f of alpha. But what is gamma? Gamma is actually, so this implies alpha minus a gamma belongs to f of alpha. Alpha definitely belongs to f of alpha. A is in f, gamma is already in f of alpha. So alpha minus a gamma belongs to f of alpha. And that means beta belongs to f of alpha. Because alpha is equal to beta plus a gamma. So that implies both beta and gamma belongs to f of alpha, implies f of alpha beta is equal, sorry, f of beta gamma is equal to f of alpha. So we can extending this to finite number of times, we get E is equal to f of alpha. Because E is a finite extension of f, so you can always write it as f of alpha 1 dash dash alpha n. We took two of them, that is beta and gamma, and found that it is this. Then you keep on extending it. Then you will get E is equal to f of. This is a very important, very strong, powerful theorem. Very powerful theorem, this one. So let us do a corollary of this theorem. We'll start with a result that we proved earlier. Every finite extension of a field with characteristic 0 is perfect. Perfect means every finite extension is separable. So that means every finite extension of a field with characteristic 0 is separable. And what does that mean? That means for every finite extension E of a field F with characteristic 0 there exists an alpha belongs to E such that E is equal to f of alpha. This is where we are employing the primitive element theorem. And what does that mean? This is called simple extension, right? So we'll see for every finite extension of a field with characteristic 0 is a simple extension. For example, if you take q of root 2 comma root 3 comma root 7 comma root 11, this is actually an extension of q and this is characteristic 0, then the primitive elementary theorem says that this can be written as q of alpha. So this extension is always a simple extension. Let us do some computational problem using the primitive element theorem. So find alpha such that q of alpha is same as q of root 2 comma root 3, q of root 2 comma cube root of 2, q of I comma cube root of 2. So let us start with this first one. Q of, see, our aim is to find an alpha in q of q root of 2 comma root 3 such that root 2 belongs to q of alpha and root 3 also belongs to q of alpha. So first of all, that element has to be in here. Then each of these elements are they should be in the simple extension of Q alpha. So let us consider this element. Let alpha is equal to root 2 plus root 3. Because you know that in the when you are proving the primitive element theorem, said alpha is equal to beta plus a gamma, a linear combination of this. This is our root 2 and this is our root 3. And we are taking a is equal to 1 here. So let us see whether we can. So if alpha is equal to root 2 plus root 3, then alpha definitely belongs to Q of root 2 plus root 3. What is actually Q of root 2 plus root 2 comma root 3 is equal to A0 plus A1 root 2 plus A2 root 3 plus A3 root 6, where AI belongs to. So definitely if this is equal to 0, so A0 equal to 0, A3 is equal to 0, A1 is equal to 1, A2 is equal to 1, then that means root 2 plus root 3 belongs to this. So the first part is done. So we need to find out how we can do the second one. So what is alpha square? It's equal to root 2 plus root 3 whole square. That is 2 plus 3 plus 2 root 2, 2 root 6. And that is 5 plus 2 root 6. What is alpha cube? Root 2 plus root 3 times 5 plus 2 root 6. And that is 5 root 2, 5 root 3. Then this is going to be 3 root 3, sorry, 4 root 3, sorry, 2 root, 4 root 3. Because this is going to be 12, so yeah, 4 root 3 plus, this will become, 3 will come out 6 root. So that is equal to what? This is actually 11 root 2 plus 9 root 3. Now alpha cube is this. So if alpha belongs to Q of root 2 plus root 3, alpha square and alpha cube all will belong to this. Or so alpha square, alpha cube also belongs to Q of alpha. Okay. Now alpha cube is equal to 11 root 2 plus 9 root 2, and alpha is equal to root 2 plus root 3, 9 root 3. So if you multiply this by 9 and subtracting it, alpha cube minus alpha, 9 alpha, this will go away. So this will be 9. So it will be 2 root. So root 2 is equal to alpha cube minus 9 alpha by 2. This belongs to Q alpha. And what is alpha? Alpha is equal to root 2 plus root 3, and that belongs to Q of alpha. Root 2 is already in alpha. So root 3 is equal to alpha minus root 2 belongs to Q of alpha. So you have root 2 belongs to Q of alpha and root 3 also belongs to Q of alpha. So alpha is our primitive element. So Q of root 2 comma root 3 is equal to Q of root 2 plus root 3. This is not unique. You can find different numbers also, but this is one of them. So we'll do the second one. Q of root 2 comma cube root of 2. Again, we need to find out alpha. Need to find an alpha belongs to Q of root 2 comma cube root of 2 such that root 2 belongs to Q of alpha and cube root of 2 belongs to Q of alpha. Here, what we do is, what is root 2? Root 2 is actually two to the power of half, and cube root of 2 is equal to 2 to the power of 1 by 3. Right? So, we are trying to find a number which goes in both, like a kind of a common factor. So if you take alpha is equal to 2 to the power of 1 by 6, that is the product of these two, then we need to show that this belongs here and also this belongs to, root 2 belongs to Q of alpha and cube root of 2 belongs to Q of alpha. So this is actually equal to 2 divided by 2 to the power of 5 by 6. And this belongs to Q and this belongs to Q of, so this actually, and 2 belongs to Q. 2 to the power of 5 by 6 equal to cube root of 2 times cube root of 2, and definitely that belongs to Q of root 2 comma cube root of 2. So that implies alpha belongs to Q of root 2 comma cube root of 2. Now we need to show that root 2 belongs to Q of alpha. So root 2 is equal to 2 to the power of 1 by 2, that is equal to alpha cube, because this is actually 2 to the power of 1 by 6 to cube, and that is equal to alpha cube, and that belongs to Q of alpha. And cube root of 2 is equal to 2 of 1 by 3 is equal to 2 to the power of 1 by 6 to square, and that is equal to alpha square, and that also belongs to Q of alpha. So Q alpha is equal to 2 to the power of 1 by 6 is the primitive is a primitive element of q of root 2 comma cube root of 2, or you can say cube root of root 2 comma cube root of 2 is equal to q of 2 to the power of 1 by 6. The last problem in here is q of I comma cube root of 2. Here what we are going to consider is, see, there is no common factor here. So what we are going to do is, let's take the product of this. So let alpha is equal to I cube root of 2. So definitely alpha belongs to q of I cube root of 2. No problem. Now we need to show that I belongs to q of alpha and cube root of 2 belongs to q of alpha. What is alpha square? Alpha square is equal to minus now let us take alpha cube. Let's take alpha cube. Alpha cube is what? Alpha cube is minus I times 2. And alpha cube, so this is actually, this definitely belongs to q of alpha because it's alpha cube. So I is equal to minus alpha cube by 2. That also belongs to q of alpha. Right? Now we need to find out cube root of 2 in terms of alpha. Alpha is what? Alpha is equal to I cube root of 2. So if we square this one, minus 2 to the power of 2 by 3. Right? So 2 to the power of 2 by 3 is equal to minus alpha square. So 2 divided by 2 to the power of 2 by 3 is equal to minus 2 by alpha square. What is this? This is actually 2 to the power of 1 by 3, and that is equal to 2 by alpha square. And this is nothing but cube root of 2 is equal to 2 by minus 2. And definitely that belongs to q of alpha. So both I and cube root of 2 belongs to q of alpha, implies alpha is a primitive element of q of I comma cube root of 2, or cube root of I comma q of I comma cube root of 2 is equal to q of I cube root of 2.